Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for my part is introduction to Vapour compression refrigeration system. This system is widely used in refrigerators, air conditioners and heat pump. Its main function is to transfer heat from a low temperature to high temperature. The system works in cycle involving key components such as compressor, condenser, expansion valve and evaporator. Many vapor compression systems operate with a COP, coefficient of performance, between 2 to 4. However, this efficiency is often limited due to several issues such as high power compression, power consumption, pressure drop, heat loss, and the use of outdated or fixed speed component. To overcome this challenge, we look into modern improvements such as variable speed compressor that adjust based on cooling demand, the use of subcooling to boost efficiency without extra output, switching the environmental friendly refrigerant, and the last one is integrating renewable sources like solar power. Our objective in this project is to improve the system COP from 2.5 to at least 4, achieving better energy efficiency, lower cost and reduce environmental impact. For proposed design and system modification to enhance the efficiency of the refrigeration cycle, we are introducing two key improvements: multi-stage compression with intercooling and subcooling of liquid refrigerant. In the first improvement, we divide the compression into two stages with an intercooler placed between them. The intercooler reduces the refrigerant temperature before the second compression stage, which lower the overall work required and improve system efficiency. The second enhancement involves subcooling the refrigerant after it leaves the condenser and before it enters the expansion valve. This increases the refrigeration effect, allowing the system to absorb more heat without increasing the mass flow rate. In addition to standard component, we improve system. We include an intercooler, a subcooler, and an optional reservoir tank for better refrigerant management. With this modification, we can increase the COP from 2.5 over 4.0. This result is lower energy consumption and longer equipment lifespan. However, this improvement do come with some challenges such as higher initial investment, increased system complexity and need more to process control. The benefit in efficiency, cost saving and sustainability make this modified system a practical and forward-looking solution despite of those challenges.
Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today I would like to present about the calculation. So for the current ideal vapor compression refrigerant skirt, refrigerant use refrigerant 134A as the working fluid as the operate on the ideal vapor compression refrigerant skirt between 0.12 and 1.2 MPa, and the mass flow rate of the refrigerant is 0.05 kilo per second. So, first we must take the information given like the evaporator pressure 0.12 MPa, condenser pressure 0.12 MPa, and the mass flow rate 0.05 kg per second. And firstly, we must draw the TS diagram of the current process. So, this is the TS diagram for the current process. Okay, we go to find the enthalpy at the state 1. So we use the table twice to find the boost of enthalpy. So H1 equal to Hg at the 120 kPa and equal to 236.97 kilojoule per kilo. So S1 equal to 0.94779. Since the state 3 is saturated refrigerant, therefore the table A12 is used to determine the enthalpy. So H3 equal to HF at 1200 kPa, and we got the 117.77 kilojoule. So since the process 3 to 4 is the constant enthalpy expansion, so it can be said the enthalpy at the state 3 is equal to enthalpy at the state 4. So H3 equal to H4. And since the refrigerant is at the compressor as the superheated vapor at the state 2, therefore table A3 is used to determine the H2. So to find the H2, we do some interpolation before they click the before they check the table A13 at the 1.0 MPa. So the value S1 equal to S2. So we get the H2 285.20 kg per kilo. So to find the COP current ideal vapor compression refrigerant skirt, we use the formula COP equal to QL over W in. So the COP must use the M flow rate and H1 minus H4 divided by H2 minus H1. So the COP for the current system is 2.05.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Rizqal Syam bin Ramlan. My metric number is DD230054. And in this presentation, I'm going to present about the calculation of our improved ideal cycle efficiency with multi-stage refrigeration cycle. So basically, in this case, we're going to use the refrigerant R134A as our working fluid, and each stage it will operate in ideal conditions. So as you can see in this slide, here is the TS diagram and the table of enthalpy and entropy. So for the value of enthalpy for H1, we're going to refer the pressure table at 400 kilopascal, and we will take the value for Hg. So after referring the pressure table at 140 megapascal, 140 kilopascal, the value of Hg is 239.16. We will also take note for the value of entropy, which is Sg, as the value of S1 is 0.99456. The value of S1 will be going to be the same as S2, and then we will refer the A13 tables and we will interpolate using the pressure table 0.14 megapascal. After completing the interpolation, we got the value of H2 is equal to 260.62. Next, we will find the value of H3 and H4 at the table of A12 pressure table. So at the pressure of 400 kilopascal, we will take the HF value and we will get 63.94 for H3 and H4. On the same pressure, 400 kilopascal, we will take the value of Hg for the value of H5. So after referring the table, H5 is equal to 255.55. Not just that, we will find the entropy value, which is S5 and S6. After referring the table, the value of Sg for the value of S5 and S6 is equal to the value of Sg at 400 kilopascal, which is equal to 0.92691. And to complete this table, we will find the value of H7 and H8 at the pressure of 800 kilopascal on pressure table. So after referring the table, the value of HF is equal to 95.47 for both H7 and H5. After completing the enthalpy and entropy table, we will continue the journey to find the coefficient of performance by finding the flow rate in the lower cycle. So we will use the formula of m dot A times H5 minus H8 equal to m dot B times H2 minus H3. After we insert the value for m dot A, H5, H8, H2 and H3, we will find the value of m dot B, where it is equal to 0.195 kilogram per second. Next, we will find the value of QL by using the formula of m dot B times H1 minus H4, and we will get QL is equal to 34.2 kilowatt. And last but not least, we will find the value of W in, where we will use the formula of W in A plus W in B, and we will found the value of W in, which is equal to 6.652 kilowatt. And finally, we can find the value of COP by using the formula of COP, which is COP is equal to QL over W in, where we already found the value of QL and W in, and we will get the COP is equal to 5.141. So this is proof. The theory is proof where the multi-stage can improve the efficiency of ideal cycle refrigeration system. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azul Helmi bin Abdullah. My 3ID CD240069. So right now I will present to you about the discussion. In this project, we will discuss 6 points. First, COP before and after modification. Initially, our refrigerant system operate with a coefficient of performance or COP of 2.50. This is typically value for a single stage vapor compression cycle. However, it also means that a lot of electrical energy is used without delivering maximum cooling. After implementing our purpose enhancements, which is include two-stage compression, intercooling and subcooling, we successfully increased the system's COP to 5.141. That's an improvement of more than 100%, indicating a major gain in energy efficiency. Number 2, rationale for two-stage compression. One of the most important decisions in our project was to switch from a single stage to a two-stage compression. Why? Because in a single stage system, the compressor needs to lift the pressure all the way from the evaporator to the condenser. This leads to high discharge temperature, more energy usage, and faster wear on component. In a two-stage system, we divide the pressure lift between two compressors. This reduces the pressure ratio in each stage and helps the compressor operate more efficiently. To make the system even better, we insert an intercooler between the two stages. This removes excess heat after the first compression, lowering the refrigerant temperature and entropy before it enters the second compressor. This step reduce the total isentropic work required. We also use the following formula to determine the optimal intermediate pressure. The square root of evaporator pressure multiplied by condenser pressure. This ensures a balanced compression ratio between the two stages. Number 3, thermodynamic performance. From a thermodynamic perspective, the improvements in our system came from two key processes. First, intercooling, and second, subcooling. First, intercooling reduces the refrigerant's temperature after the first compressor. This lowers its entropy before second stage, which reduces the amount of isentropic works need to reach condenser pressure. It also helps to avoid overheating and improve overall stability. Second, subcooling is applied after the condenser. It lowers the temperature of the refrigerant below its saturation point. This increases the enthalpy difference in evaporator, allowing more heat to be absorbed per kilogram of refrigerant. In other words, we get more cooling effect without increasing the mass flow rate. Together, these two processes significantly raise the system overall efficiency. Number 4, component impact. Our design modifications did not just improve the thermodynamic performance, they also affected how the system components operate. By using two compressors, each one now works under a lower pressure ratio. This reduces mechanical stress, heat generation, and the risk of the component failure. The intercooler also plays a crucial role in protecting the second compressor by lowering the temperature of the incoming refrigerant gas. This extends the lifespan of the compressor and helps maintain stable operation. Meanwhile, the subcooler ensures that the refrigerant entering the expansion valve is in a fully subcooled liquid state. This prevents premature evaporation and improves the evaporator's ability to absorb the heat efficiently. Number 5, advantage versus challenge. Let's now look at the advantage and challenge of our modified system. The most obvious advantage is the significant increase in COP, which means the system now requires less energy to provide the same or even more cooling. This can lead to lower operating costs and a smaller environmental footprint. Other advantages include reduced wear on compressor and better thermal control, which result in longer equipment life and improved reliability. However, we also identify several challenges. Adding a second compressor, intercooler, and a subcooler increase the system's complexity and initial installation costs. It also requires more advanced control system and regular maintenance. These are important consideration when applying this design to real-world application. Number 6, future improvement. For future improvements, we suggest 3 main areas. First, the usage of eco-friendly refrigerant, such as R1234YF or carbon dioxide CO2, to reduce the system environmental impact while maintaining good thermodynamic performance. Second, the integration of renewable energy source, such as solar panels, to power the compressor and further reduce energy costs and depends on the electricity grid. Third, the implementation of AI-based smart control system. This system can monitor real-time cooling demand and automatically adjust compressor performance to optimize energy use. This will make the system even more responsive, efficient, and cost-effective. In conclusion, the modification of our refrigerant system using a two-stage compression cycle enhanced with intercooling and subcooling resulted in a significant performance boost. The system's COP increased from 2.50 to 5.141, which confirms that the thermodynamic improvement can deliver major gains in both energy efficiency and cooling capacity. Despite complexity and cost, the system proved to be an worthwhile investment, especially for industrial scale applications such as HVAC systems and cool storage. where energy savings translate to real operational benefits. Looking ahead, there is strong potential for further development by adapting eco-friendly refrigerants, implementing AI-based control systems, and integrating renewable energy. This system can evolve into a sustainable and future-ready refrigerant solution. That's all from us. Thank you.